Today we started looking at the Z transform, because as we see, transforms does give us a lot of information about a system and signals, and we'll see that it becomes very useful, especially when we describe our LTI system using the difference equation, which is actually a very convenient way of representing a system, especially when you're talking about filtering, design of filters. So we'll see that. I'll just look at the properties of the Z transform. Again, we started looking at them. And of course, because I'm aware you have done Laplace transform, probably we should be comparing this with the Laplace transform. So whenever you look at whatever you know about Laplace, you can apply it here. In that the Laplace transform, I think, is basically Cartesian. You know, we don't call it Cartesian coordinate. Of course, we call it we don't call it Cartesian plane. We call it this plane, but it's also considered Cartesian, you know, as opposed to Z, which is more of the, it's more polar. Yeah, I think the Z transform is polar, while the Laplace transform is Cartesian. Yeah. It's considered to be similar to the Cartesian plane, so we actually say it's Cartesian. So this plane, in our case here, we have the imaginary Z, yeah, and of course we have the real Z. So I think we have, no, I think it's sigma. Yes, let's bring has got S, and this is plus the omega, this is the imaginary, yeah. So whatever this side is similar to is equivalent to this area, which is bounded by this circle of radius 1. Yeah. So as you say, when you talk of the ROC, it cannot contain any poles. So whatever, all the properties of the Laplace, where we say, I think the poles cannot even be on a certain side. For example, the poles cannot be in the ROC. So even the poles for this cannot be in the ROC. Yeah. And I think I don't know whether you can be able to see the connection if you have done already ROC for the Laplace transform. Maybe you can be able to connect. But maybe as we go through the properties, you see things which are similar to the Laplace transform in the analog domain. Oh, it's okay. So the ROC of the Z transform is a ring or disk in the Z plane. I think we have plotted it here. So the ROC will be a disk. So the ROC will be either outside that disk or inside that disk, or it will be between two disks. We are going to see the different cases. The ROC of an LTI stable system contains the unit circle. It means it must be, the ROC must have part of this. Yeah, so it is must have part of this. When the Z transform is rational, then the ROC is bounded by poles. It's rational, it means that both denominator and numerator, or extends up to infinity. If xn is infinite duration causal sequence, the ROC, this is what we were saying, depending on the sequence, Z will be greater than A, is the exterior of a circle. I mean, that is the ROC will be, if this is A, if let's say this is a circle of radius A, the ROC will be, that is, if it's an infinite sequence, that's what we are saying. Yeah. And if it's an infinite causal sequence, and of course, if it's anti-causal, which means it's a left-sided, it's a left-sided sequence, yeah, then the ROC will be whenever that B is, it means it will be on the inside as opposed to the outside. Yeah, if this is the circle of radius, I mean, if this is a circle of radius B, yeah, it means it will be inside and not outside. So infinite duration causal sequence on the outside, and this will be on the inside. If X is a finite, we are talking about infinite, now it is a finite causal sequence or a right-sided sequence, but finite, then the ROC is the entire plane except at Z is equal to 0. Here Z can't be 0 because if it is a right-sided sequence, then it means it will be having Z to the minus n, which means 1 over Z to the n, because n is positive, right-hand sequence. So this cannot be 0. If this is 0, then the sequence exposed to, the Z transform goes to infinity. Yeah. If Xn is finite anticausal sequence, left-sided sequence, then the ROC is the entire plane except at Z is equal to infinity. I mean, it makes sense. It's only when Z is equal to infinity, because that would mean that because that is Z n cannot be infinity, then it will go to infinity, because it will be Z. If it's negative, it will be Z to the minus n, which is Z to the n. Yeah, if this n is negative, yeah, Z to the minus n becomes Z to the n, and therefore it will be entire Z plane except at Z is equal to infinity. Yeah, we'll see with real sequences. If Xn is finite, two-sided sequence, that is non-causal, then the ROC is the entire plane except at 0 and at infinity. And we are saying that it's only delta n as the impulse sequence which has got, whose ROC is the entire Z plane. no exceptions. Yeah. So these are the different scenarios. These are causal finite sequence converges except as z is equal to 0. Anticausal converges except z is equal to infinity. Non-causal converges except as z is equal to infinity and 0. And here we have an example. This is a causal sequence. This is a zeroth sample. So x of z is a negative infinity to positive infinity, x of n, z to the minus n. In this case, we know it goes from 0 to 3. Is a finite sequence. So if you expand this becomes x of 0, z to the minus 0, that is n, minus 1, x of 1, x of 2, x of 3. And of course, this is the samples, so it will be 1, x of 0 is 1, times 1, because z to the power of 0 is 1. This is 2 times z to the minus 1, which is 2 over z. This is 2 over z squared. This is 3 over z to the power of 3. So the ROC is the entire z plane except at z is equal to 0, because once z is equal to 0, this becomes infinity. So it's the entire plane except z is equal to 0. Yeah, that's the ROC for this sequence. For the for the z transform of this sequence. Yeah. This is anticausal. You can see this is the 0th sample. This is minus 3 sample, minus 2, minus 1, 0. So this goes from minus 3 to 0, x of n, z to the power of minus n. So if we replace n, so this is the first one is x. Yeah, of course this is 1. X of minus 3 is 1 times z to the power of minus n. N is minus 3. So this becomes z to the power of 3. Then this becomes minus 2. This is z squared. This is z. And this is 2. Yeah. And you can see x z converges except as z is equal to infinity. So that's for a causal. This is for an anticausal sequence, and this is for a causal sequence. Non-causal, actually just what we had talked about when we talked about the properties of the ROC, of the Z transform. So this is non-causal. It has the right. It has samples on the right side and those on the left side. So this goes from minus 2 to 1, x of n, z to the minus n. If you replace, if you put in the values of these samples for the x's, and then put the values for n, then we are going to get that. And you can see it converges except at 0 and infinity. Infinity because of this term and this term, 0 because of this term. Yeah. So far, so good. I think we understand, now everybody understand the concept of Z transform. Yeah. Before we see its importance. Yeah. It's actually very easy to work with because you don't have the Wn, e to the j omega or e to the j 2 pi and k over n. Yeah, so it's just been with the z, so it makes it quite easy to deal with. Yeah. So the Bibo stability for discrete time systems. So we say that a system is Bibo stable if any bounded input to the system will result in a bounded input. And for that, if you do the summation of all the samples of Hn, you're going to get negative infinity, but we are talking about the magnitude of Hn. Yeah. So it doesn't matter even if the samples are negative. That's what we are saying, even for the negatives, for n being negative. And those values may be negative. Yeah. That will be, you have to take the magnitude. Because you could be having samples like +3 and -3. That's why we are saying you have to take the amplitude of Hn. So this, then you sum them from negative infinity to infinity. It must be less than infinity. Yeah. If a system has that, obeys this criterion, then we can say it is Bibo stable. And the Z domain condition for Bibo stability is that the ROC must contain the unit circle. Yeah. So if the ROC is outside the unit circle, then a system is not stable. Yeah. For a causal system, we want to see, for a causal system, what conditions it must meet for it to be stable. First of all, a system is said to be causal if its response depends on the present, past input, and past output, but not the future input and future output. That's how you describe a causal system. And for stability, ROC must contain the unit circle. And a system is causal if and only if the ROC is exterior of a circle outside the outermost pole. Which means a causal system can only be stable if and only if all the poles of Hz lie in the unit circle. Yeah? Because to be stable, it must include the unit circle, ROC. And if it's causal, all the poles must be lie in the unit circle. Yeah. So a system is causal, so it must be outside the unit circle. So if you have got your poles here, then the ROC must be outside. That is for causal. Yeah. But for it to be stable, this must be the unit circle. This is the unit circle. This is the unit circle, this one. Must be part of the unit circle, which means you cannot have poles outside the unit circle if the system is causal and stable. Yeah? That's the only way you can meet these two conditions, by making sure that your ROC starts inside here. It means the poles cannot be in the ROC. So it means it must be inside the unit circle. Yeah. So for this to be stable, all poles lie within the unit circle. Yeah. Because ROC must contain the unit circle. So if you meet those two conditions, then you meet this condition. That's the only condition for a causal system to be stable. Yeah. So I hope so far so good. Yeah. The logic behind that. So causality and stability, I think here we're just having an example. So you have x of n is equal to a half to the power of n, e of n, and that to the power of n, e of n, e of n. Of course, what this one is telling you, whatever you have u of n, it just means this is causal, and this is causal because of the u of n. U of n, make sure that whatever you have does not. This means is the right hand is the right hand sequence. Yeah. Now, this is if you have a to the n. Yeah. If you have a to the n as they are xn, xz should be what? So e to the n. Oh no. Yeah. Should be z over z minus a. Yeah. This one nobody expects you to remember. I think we have, let's see whether we have a z. Oh, I think I have a z transform table somewhere. Yeah, that's a z transform table. So you have a to the n. Where is it? So, a to the n. Yeah, is that one. So you have a to the n. U of n just means a sequence. I mean, is a the u of n is that a to the n. U of n is that. So you just have alpha here. So in our case, a is a half. So this simply, so if a is a half, it becomes 1 over 1 minus a half, because a is a half. Oh, z. I think this will be z. Was it 1 over z? Where are we here? Z to the minus 1. Z to the minus 1, which is simply multiplied up by z and down by z, so it becomes z over z minus a half. Yeah. So this becomes z over z minus a half. And of course, this is z over z minus a third. So it means z and here the magnitude of z must be greater than a third. So we have to plot the ROC, and the ROC will be this. It must be the common ROC. So the common ROC will be, because one starts from here and one starts from here, so the common ROC is from here. the poles are contained within the unit circle. Yeah. So this is a system. Yeah, of course, x of z is linear. That's why you can do this. If x of then is this plus this, then z of x of z is this plus this. Yeah. Because z transform is linear. So this system is causal and stable. Of course, it is causal the moment you have u of n. Yeah. If this is describing a system, then it is causal and stable. Yeah. Because that could also be describing a signal, but if it's describing a system, that is a causal and stable system. Yeah. So I think we have the common R of ROC. Oh, where did I get 0.5? Yes, it's outside 0.5. Yeah. So the system is causal and stable, and these are the conditions for causal and stable. So the question you can get, of course, is you can be given an expression giving the value of x of n, and then you're asked whether the system is causal and stable, and you have to work out that. Yeah. This is another transform unit step function. Yeah. So UN, this unit step function is equal to 1. U of n is equal to 1, or n is equal or greater than 0, and is 0 elsewhere. So you got to find out the z of u of n, which is uz. This will be negative infinity to infinity, u of n, z minus n, but u of n is equal to 1, or 0 to infinity. So this is the same as 0 summation from 0 to infinity, 1 times z to the minus n. But we know this, but we have just used it. Yeah, a to the n is just 1 over 1 minus a. Therefore, u of z is equal to n is equal to 0 to infinity. So this is the a. So it's simply 1 minus a, which is that. So that is the z transform of the unit step function. Yeah. This is not unit. The transform is not unit. Right-sided sequence. Yeah. As this, but just a right-sided sequence. So find the transform of the sequence upper to the n un, which means it's right-sided because of this. So x of z is n is given by n is equal to negative infinity to infinity x of n z to the minus n, which is simply, x of n. It's just alpha of n, because I mean, if you consider from 1 is 0 to infinity, then it's simply 1. The value of this is 1, so long as your limits are from 0 to infinity. Yeah, you get that? So that, again, you use the same formula, because the moment you have 0 to infinity, then you use that sequence of this one. You use this. Always remember this, it makes work very easy. So whatever it is, when you're given u of n, it means you can always look, you can always consider your limits of summation from 0 to infinity, and therefore you can be able to reduce the sequence into this form, the closed form. Yeah. So there we are. So that, I hope so far everybody is okay with this. So the sum will converge. Oh, we are just talking about this. So this sum will converge when this is less than 1. Yeah, when this is less than 1, it means then Z is greater than alpha. So expressing Xz in terms of positive power, then we have this. That is x of z is z over z minus alpha. So 0 at z is equal to 0, and the pole at z is equal to alpha. And that C is the exterior of a circle. I think, remember this one of the property? We said that when, because this has, you see, this is what it is. This is an infinite sequence. Yeah. So if it's an infinite sequence, that's what you get. Yeah. And the ROC is exterior of this circle, sketched by alpha. Yeah. And that's what you're seeing. If alpha is here, the alpha is inside here, then this system would be a stable system. Yeah. Because this is a part of the circle. Yeah. It has to be, the ROC must be exterior of this pole, and this pole happens to be inside here. So this system will only be stable if alpha is less than 1, and of course it makes sense. If alpha is less than 1, it will converge. Yeah. Otherwise, it will just diverge. Yeah. So does anybody have a problem with the region of convergence? Let's do another one example. I don't know why I put this. Oh, this is a unit. Oh, this is okay. The unit left side in sequence. Yeah, it is u of minus n minus 1. So this u of n minus 1 is minus n minus 1 is equal to 1, or n is equal to infinity to minus 1, and is 0 otherwise when n is greater or equal to 0. So the z transform of this is this, which of course you can separate it into 2. Minus n is equal to minus infinity to minus 1. 1 times, because this will be 1 for here, times z to the minus n, and 0 to infinity, 0, because it will be 0. It's a left-hand sequence, so it is 0 this side. So this is 0, so this simply becomes this, and that there is a time reversal property. It means that is the same as the summation n is equal to 1 to infinity z of n. Yeah, you can just reverse this, and you get this equal to that's the time reversal property. So this changes from 0 to that, because of course time reversal, it means the n becomes negative n. It makes out of sense. Yeah. So the time now will reverse, and you're not going to go from negative infinity to minus 1. You're going to go from 1 to infinity. That's the time reversal property. just n becoming minus n. So we are saying, so that we can't, but we know this is equal to this. So it's simply the Z transform of this is simply this. Yeah. Yeah. It is this. It becomes this. Yeah. So you have to remember all those the time universal property. That's one of the most important one, and where you're converting the geometric sequence, geometric series into a closed form expression. Oh yeah, this is also unit. So ROC, I think we are doing the same one. We have seen is equal to this. So the ROC is 1 over Z has bigger than 0, this one. If 1 is greater than Z, or Z is less than 1. So that's why we are finding the ROC is interior of the circle. Remember I said about an infinite left-sided sequence. Yeah? Or what you're calling an infinite anticausal sequence. Where the ROC is inside, it's not inside the unit circle. In this case, it's unit circle because the unit circle is 1. So it's actually just inside the unit circle. This is the unit circle incidentally, just because of this 1. Yeah. So, but it's inside some value B. In our case here, it happens to be just inside the unit circle. Yeah. I hope we are all together with the ROC. I think we are almost through with ROC. Then we are doing another example here. We have the Z transform of this. Let me cosine here. So you're given as ROC of this, and I think here we are using the linearity of the Z transform. So here you can open up, it simply becomes 1 over 5 to the n u of n minus 1 over 5 to the n u to the n minus 5. Yeah, so the Z transform of this, I think I can just put it there, is the Z transform of this minus the Z transform of this. And for most of these Z transforms, you'll be provided with the Z transform table, so you can make reference. So you don't have to remember anything. Yeah. So that's what you have. Remember, the Z transform a to the n is this. So for this is your a. The n is 2. So it will be that this will be 2 over z. Yeah, because is z over z. Oh, this over z, not over 2. Oh, is z over z minus a. So this is not 2. Oh, why was I? Oh, sorry. Oh, this is n. So about that, this is n, not 2. Which is simply z over z minus 1.5. And then minus the z transform of this, which you can bring this out and then have z transform. Yeah, because there is, you can write this in this way. Yeah, so that you have got 5 outside, and then you have this n minus 5 with n minus 5. Why we're doing this? Because we want to apply the time shifting property. That's why we want to write it in this form. So we are bringing this out. Yeah. So the Z transform of this is simply this. Yeah. Is Z the minus n naught x of Z. Yeah. So it's simply Z to the minus 5x of Z. That's what we are saying. If you have this, it is simply this. Of course, x of Z is a is a what would you call it? Is a Z transform of x over n. So we are saying that will simply become that. Then we remove this Z to the minus 5 here, and this becomes this is the Z transform of this part, of this particular part. Yeah, this one. Yeah, so we get that. So there we are. So here we're just applying linearity. So whenever you're given two addition of two, where x is composite, it has got two parts. You can simply find the Z transform of one and add to the Z transform of the other one. So any question before you go to the Z, before you go to the inverse Z transform, the inverse transform, inverse Z transform. If there are no questions, the inverse Z transform is defined by this x of n is 1 over 2 pi j. This is a contour integration. Yeah. X of z, z to the n minus 1 dz. So just from this contour integration, this becomes a bit too complex. So usually we don't use direct conversion. We don't do direct conversion of xn because of the complexity of this, doing this contour integration over a complex plane. You can see it's over a complex plane. It's very complex. So usually we don't have that. We don't use direct. Like the way we use direct DFT, direct DTFT, a direct IDFT, direct IDTFT. We don't do that with the Z because of this complicated integral. So the two main approaches are long division and partial fractions. Yeah. And of course, these are important because they will become very handy when you're designing filters. Yeah. So you need to understand how you do it. When you design filters, you're going to find there will be cases where you need to apply one of these methods. Yeah. So in this case, x of z is what this you're given this as the transform. You're given the transform, and you want to get back your x of n. So if you're given this 3z squared plus 2, yeah, this one you can simply put it as this z squared plus 0 z to the 1 and 2 z to the 0, and this simply x. This simply so these are the three. So this is x minus 2, x to the minus 2, n is minus 2, x to the minus 2. This is x to the minus 1. This is x minus 1 sample, and this is from x, the 0th sample. When you see this is the 0th sample. So this is simply 3, 0, 2, and this is the 0th sample. Yeah. We are saying when you see this, it simply means 2 to the z to the power of 0. So that is a 0th sample. Yeah. So this is straightforward where you're given something like this. Yeah. That is your x of n. Here you're given 3 plus 2 to the minus 1. Remember, this is always z to the minus n. So if you have this, it means here n is 1, n is 0 here, so means this is a 0th sample. Yeah. And this is that sample where n is equal to 3. Yeah. So this simply is you can use, that's one method. This is direct. It's not direct applying this formula, but it's direct because of linearity. You can just do the z transform of each of the inverse z transform of each of these, and then you add them. Yeah. So long division, you're given this. Of course, some of them will be such a way that you can be able to check on the table and see that this, I think if you go to the table, you can find this. Because this is simply what? This is 1 over 1 minus 0.5 z to the minus 1. So I think we have this. This should be actually already, you can see. Otherwise, if you check from the table, you'll find that it is equal to this. Yeah. Yeah. This in this form, I think we can get it here. This one here. Where is A? Here. Where our A is 0.5. Yeah. So it means the 0.5 to the power of n. Because n, A or alpha here is 0.5. So you can be able to directly, if you're not able to work out, if you just want to find, if that's not what you are told to work out, then you can simply refer to the table. But if you are told to determine or find, if you are checking to do something else, then you can just check. But if you are being told to find using this method, yeah, then you'd have to use that method. So using long division method, let's see how we get it. This is z minus 0, z divided by z minus 0.5. It goes once because of z minus 0.5. So this is 0 minus 0.5, so it is 0.5. So this can go how many times? Can go like this. It can go this number of times. Yeah, it's interesting. because of 0.5, we're trying to make this 0.5. So it can be 0.5 z to the minus 1. So you get your 0.5 minus this. Yeah. Then this will go 0.25 z to the minus 1. So this can go 0.25 times to the power of minus 2, so that you get that. And this can go 0.25 z to the minus 1 minus 0.125 z to the minus 2. So you can see this one is actually an infinite sequence. Yeah, it will not end. It will just go on becoming like that. And if you look at this, you can see that this is simply x of n is 0.5 to the n. It's an infinite sequence. Yeah, it is a bit easier to see with this. Sometimes it can be complicated to see from here. But the moment you have this format, then you can just take it from the table, unless you are trying to work it out in this form, long division. The next one, the other method, which is the common method, the easiest method, especially where you're given the transfer functions, is having a denominator, a numerator, which has both poles and zeros. You have zeros and poles. Then this is a method that is normally used. You have been asked to find Hn. The first thing you do is you want to put it in a form which you can simply check from the Z transform table. Yeah. So what you do is, you can see this is Z to the power of 2. You must reduce it to Z plus something. Yeah. So you divide by Z. I'm sure this one you could have done it actually with the Laplace transform. Only instead of S, now you have Z. Instead of Z, you have S. You could have done it in Laplace transform when you're doing. Yeah, I'm sure you have done it with Laplace transform. It's the same method. Yeah. So divide by Z. Because yes, sometimes you can be asked to design a filter whose transfer function is expressed as a function of S. And you have to do some bilinear transformation to get to Z. Yeah. So you have this. So you have divided by Z. So if you divide by Z, of course, what you're going to get is this becomes Z plus 2 over this. And this, you can see, works out to Z minus 1 times Z minus 2. Of course, if you're given this, it must be something that works out to this. Yeah. So if you have this, then what you want to find out, you want to put it in the form A over Z minus 1 plus B over Z minus 2. So what you do is, you can work this out. You can put it under, you can have this in a common denominator, Z minus 1 into z minus 2. Of course, this will become a into z minus 2 plus b into z minus 1. So it means this is equal to this, yeah? If you create the two equations, you're going to find that this is equal to this. So that's what we're saying, this is equal to z plus 2. So you can put like terms together. So the ones with z, ez plus bz gives you that. And this other one is minus 2a minus b is equal to z plus 2. It means a plus b is equal to 1, since this term is equal to this term. So a plus b is equal to 1. Then this term is equal to this. So it means 2a plus b is equal to 2, which means you can just add this, and this becomes minus a is equal to 3. This is a, this is 0, is equal to 3. So a is equal to minus 3, and therefore b is equal to 4, and therefore you end up with this. And this, from the table, you can see that each of n is minus 3 u of n plus 4 times 2 to the n u of n. I don't know whether it was a short topic or I went very fast on it, through it. But are there any questions?
Yes, I have a question.
Yes, Samuel.
Yeah, currently in our mathematical methods class, we've been looking at Laurent series, and now looking at the transform. I kind of see they are related. Maybe could you share some insights into that? Is there a transform related to the Laurent series that we've been looking at in math?
Well, I'm not sure about the Laurent series. I mean, the last time I looked at those series was many years ago, but they look similar. But of course, we use them. You see, there you're using to simplify something or to put it in a form. But here we are going to use, but they are not related. I don't know if they are related. I don't know. I think I last dealt with those series in my maths class in college. So I can't say much about them.
Thank you.
Okay. Any other question? So if there are no other questions, just post your registration. I think that is now for today. Having it 2 hours in the morning, that was quite a lot for the day. So post your registration on the chat. And I think let's do our cut next week. Is that okay? We cover up to today. We can use Wednesday to do the cut, the 1 hour. This cut will be a physical cut. So I hope that Wednesday is okay with everybody. I think we should sit the cut because the semester is already in the middle. I don't know whether you have started other cuts or this will be the first one, but let's do the cut next week.
Excuse me.
Yes?
What about the other week? I think next week is too soon.
Oh, next week is too soon. Okay. You like a notice of 2 weeks.
Yes.
Okay. Then let's do it next week, the other week. Okay, agreed. I have no reason why I should insist on next week. So let's do it next week, but one. So with that, if you have posted your registration, you can leave